Hey y'all, this is our video for Module 4, Lesson 27. This lesson's titled Nature of Solutions of a System of Linear Equations. We'll start with the learning objectives, get into the agenda, and then get into the classwork. So our first learning objective for Lesson 27 is that students can recognize when a system has infinitely many solutions, and that's when a system has two equations that describe the same exact line. And the second learning objective is that students can use an algebraic strategy to solve a system of equations using one of two strategies. The first strategy is by substituting one equation into another, or the second strategy is rewriting expressions until they can be set equal. And this gives the exact point where the two lines intersect. So our agenda is brief. We're going to work on problems 1 through 3. Have a discussion about those problems, write down some key ideas, and then wrap up with problems 4 through 7. So without further ado, let's get into the classwork. All right, so number 1 says, determine the nature of the solution of each system of linear equations. And this is actually probably a good time to review what we have talked about in previous videos and in previous lessons. There are 3 situations that we can observe in a system of equations. And the first situation is that there's one solution. That's because there's one intersection point between two lines with different slopes. There's a second situation in a system of equations where there's no solution. And we saw that in lessons 25 and 26. And this situation happens, there's no solution when there are two lines that run parallel to each other. And they never intersect, they never cross, and therefore there's not any one point that will be a solution to both equations or both lines. So no solution. There's no intersection. Between two lines, and this part is important, with the same slope but different y-intercepts. The last possibility, actually, let's do a little sketch to show no solution is when you have parallel lines. One solution is when you have lines that intersect or cross. And that would be the solution to that system where those lines cross. These parallel lines do not cross, so there is no solution. And then the last possibility is that there are infinitely many solutions. And that happens when two equations describe the same line. And you can tell that two lines are the same if they have the same slope. And this part is really important, same slope and same y-intercept. So these are three situations that you definitely need to be familiar with for our end of module assessment, and we also need them to follow the directions for numbers 1 through 3. So again, it says determine the nature of the solution to each system of linear equations. So once we can compare the slope and y-intercept of these two equations, we'll ask ourselves, which situation is it? Is it one solution because the lines intersect? Is there no solution because the lines are parallel? Or are there infinitely many solutions because two equations actually describe the same line? All right, so finally, number 1. Determine the nature of the solution to each system of linear equations. As always, before we can compare slope and intercept for two equations, we need to have both equations in slope-intercept form. Slope-intercept form is y equals mx plus b, where m is the slope and b is the y-intercept. And if we look carefully, we can see that the second equation is in slope-intercept form, y equals mx plus b. But this equation is in standard form. Here's the ax plus by equals c. So we need to change this first equation into slope-intercept form. So we will start by rewriting that equation. 3x plus 4y equals 5. In slope-intercept form, y is the only term on the left side of the equation. So we should subtract 3x to get rid of the 3x on the left side, but we need to subtract 3x from the right side too. The positive 3 and the negative 3x term cancel out, and we can bring this 4y down. 4y equals, the order here does matter, and we have to put the term with the x first. That's the slope. So 4y equals negative 3x plus 5. Is this equation in slope-intercept form now? It's not because of this 4. How do we get rid of this 4? We divide by 4 to undo the multiplication, and we divide by 4 across the equation. So this 4 crosses out. We can just bring down the y. Y equals negative 3/4 x plus 5/4. So here's our slope for the new equation, and here's the y-intercept. So now we can compare the slope and the y-intercept and answer the question. My advice when you're doing these kinds of problems is to write slope on the side somewhere and y-intercept on the side somewhere like this. And we're going to ask ourselves, are the slopes for these two equations the same or are they different? And we're comparing this equation with this equation. So are the slopes the same? Negative 3/4 x, negative 3/4 x, they are the same. And let's write what they are, negative 3/4. And now we should compare the y-intercepts. So the y-intercept for this equation is 1. The y-intercept for this equation is 5/4. So let's write different. And we'll write the y-intercepts, which are 1 and 5/4. And now we can do this part, which says determine the nature of the solution. So we're looking to see, are these equations, is there one solution? Because the lines have different slopes. Is there no solution because the lines are parallel with the same slope but different y-intercepts? Or are the equations, do they represent the same line and maybe there are infinite solutions? So same slope, it can't be one solution because if there's one solution, there are different slopes. No solution says same slope but different y-intercepts. Same slope, different y-intercepts, that means that there is no solution. there's no solution to the equation. Oh, sorry, there's no solution to the system because the lines are parallel. How do we know the lines are parallel? Why am I saying that they're parallel? Again, we learned in lesson 26 that when two lines in a system have the same slope but different y-intercepts, that means that when we graph them, they would be parallel, not crossing each other and not sharing any solutions. All right, so here we go to number 2. Have to start with, are these equations in slope-intercept form? And I see an ax plus by equals c. That's standard form. That's not slope-intercept form. Ax plus by equals c. Here's another equation in standard form. We need to change both of these equations into slope-intercept form. We'll start with the first equation, 7x plus 2y equals -4. This, let me write slope-intercept form somewhere. Y equals mx plus b. Y should be the only term on the left side of the equal sign. So like actually in the last problem, we'll subtract the x term from both sides. The positive 7x and the negative 7x cancel out. We can bring down the 2y. 2y equals, and like I've said many times in these videos, the x term has to go first, minus 7x and minus 4. And now we have to divide the entire equation by 2 to get y by itself. These 2's cancel out. So we get y equals -7 halves x minus, and we've got to be recognizing that 4 over 2 is the same as 2. Again, 4 divided by 2 is 2. So we're rewriting this fraction as just the whole number 2. This equation is in slope-intercept form now, y equals mx plus b. And we've got to take care of the second equation, which is x minus y equals 5. Y should be the only term on the left side. Subtract x. These x terms cancel out. We bring down the negative y. The x term has to go first, negative x plus 5. Now this equation almost looks like it's in slope-intercept form, but it's not because this term, the y term, is negative. Now there are 2 ways to flip this sign around. You can either divide the entire equation by 1, or you can divide the entire equation by -1, or you can multiply the entire equation by -1. We'll just multiply by -1. Doesn't matter which side you write this on. -1 times negative y equals positive y. -1 times negative x equals positive x. -1 times positive 5 equals -5. Now we have our second equation in slope-intercept form, y equals x minus 5. Now we can follow the directions for these exercises and determine the nature of the solution. Let's, like we did in this last problem, write slope and y-intercept so we can keep track of what we're comparing. Slope, y-intercept. Now again, what are we looking for when we compare these equations? We are comparing the slope and the y-intercept to see if there's one solution, no solution, or infinitely many solutions. The slope for these equations, I'll circle them, the slopes are -7 halves x and positive x. Those are not the same. So we'll write different. And those slopes are -7 halves. And secretly in front of this x is the number 1. That's actually the slope there. And the y-intercepts for these 2 equations, I'll underline the y-intercepts, are -2 and -5. Those are also different. Okay, so different slopes, let's see. For one solution, there's one intersection point between two lines with different slopes. So that's as far as we need to go. This is really the only option for different slopes, because if there's no solution, they're the same slope. If there's infinitely many solutions, they're the same slope. So if you're looking at a system of equations and they have different slopes, you automatically know there's one solution. There's one solution because the lines have different slopes and will intersect. That's not what the system of equations necessarily looks like. That's just a drawing to help remind us that when there are two lines with different slopes, they will cross. Okay, so now we're ready for number 3. Ax plus by equals c. Ax plus by equals c. Both of these equations are in standard form, so we need to get them into slope-intercept form. So like with numbers 1 and 2, we will rewrite each equation. Y should be the only term on the left, so we can subtract 9x from both sides. We can bring down this 6y term. 6y equals negative 9x plus 3. This equation is not in slope-intercept form because we need to divide by 6 across the entire equation. The 6's cancel out. Bring down the y. Y equals, if we factor out a 3 from the numerator and the denominator, which means that we divide out a 3 from both, we get negative 3 over 2x. And same thing, if we factor out a 3 from the numerator and the denominator here, we get 1 over 2. So now we have the first equation in slope-intercept form. We'll move on to the second equation. 3x plus 2y equals 1. We have to subtract 3x from both sides. These terms cancel out. We can bring down that 2y equals negative 3x plus 1. And then we have to get the y by itself. So we should divide by 2 across the entire equation. We cancel out these 2's. Y equals negative 3/2 x plus 1/2. And now we have two equations that are in slope-intercept form. And we'll do what we did before, which is write slope so we can record our slopes, and write y-intercept so we can do the same thing. The slope for the first equation is negative 3/2. The slope for the second equation is negative 3/2. They're the same. And the y-intercept for the first equation is 1/2, and the y-intercept for the second equation is 1/2. They are the same. So now we have to determine the nature of the solution to the system. And let's see. When there's one solution, we know that they have different slopes, so we know that's not it. When there's no solution, the two equations have the same slope, but different y-intercepts. That's not what we saw. They have the same slope and the same y-intercepts. So for number 3, it must be the case that these two equations describe the same line. That means that they have the same slope, check, and the same y-intercept, check. So there are infinitely many solutions to the system. The two equations represent the same line. Okay. So now that we have completed problems 1 through 3, we're going to have a little discussion. So we'll come back to the classwork in just a minute. But let's summarize what we have discovered from the 3 examples so far. Okay, sorry. The 3 situations which we saw in the first 3 exercises was that there's one possible solution for a system, and that's true when there's one intersection between those 2 lines, and the equations in that case have different slopes. The second possibility is that there's no solution to the system because there's no intersection point between 2 lines that run parallel, like these 2, which have the same slope but different y-intercepts. And then the third possibility, the third situation that we saw is that there can be infinitely many solutions because the 2 equations describe the same exact line, meaning they have the same slope and the same y-intercept. We're going to take a look at one more system. We'll look at a few more systems, but we'll start with this one. So we'll go with example 1 here. And the 2 equations that we're going to look at in this system are 3x plus 2y. I forgot to plug my light in. It's getting dark. Hold on. I thought I was all the way set up, but I'm not. Right, lights back. The 2 equations that we're looking at, 3x plus 2y equals 5. And the second equation we're looking at is 6x plus 4y equals 10. What do you notice when you look at these 2 equations, especially when you look at the numbers in the second equation? I'll give you just a second. Okay, I hope that you notice that in the second equation, the coefficients like 6, 4, and this constant 10 are all the same as the coefficients and constants from the first equation, only multiplied by 2. So 3 times 2 is 6, 2 times 2 is 4, 5 times 2 is 10. So this means that one equation, this one, is just a scaled down version of this equation here. These 2 equations describe the same exact line, so they have infinitely many solutions. And just so that we can verify that, let's prove this using actual solutions. So let's see, we can find a solution. We'll do it this way. We can do it visually. I'm going to grab a piece of graph paper and I'm going to graph this first equation. First, it needs to be in slope-intercept form. So we'll rewrite this equation to the side. 3x plus 2y equals 5. we'll subtract 3x from both sides. Bring down the 2y. 2y equals negative 3x plus 5. And we can divide by 2, divide by 2, and divide by 2. Y equals negative 3 halves x plus 5 halves. Not a lovely example to graph. So you know what? Instead of showing you a visual, let's just start with this point, which because I did graph this earlier, I know that 1, 1 is a point to this first equation, 3x plus 2y. And we can verify that by plugging in our terms, our x and our y terms. So we have 3 times 1 plus 2 times y, which is 1, equals 5. So we have 3 plus 2 equals 5. That's true. And because these two lines are the same, I can also plug the same coordinate into the second equation, and it should show us that it's also true. So again, we'll start with this point, 1, 1. And our second equation is 6x plus 4y equals 10. We can plug in 1 for x, 6 times 1, and 1 in for y, plus 4 times 1 equals 10. 6 times 1 is 6, plus 4 times 1 is 4 equals 10. So 1, 1 is true for both of these points. And we can try another point too. So I know, again, because I was looking at this graph earlier, that the point 3, 2 is a solution to this first equation. And we'll plug it in and then we'll see that. So we can do 3x from the first equation, 3x, that's 3 times 3 plus 2y equals 5. 3 times 3 is 9, plus 2 times 2 is 4 equals 13. That's not quite right. Sorry, I forgot the negative 2. It's a negative 2. So we have 3 times 3 plus 2 times negative 2